Okay, so we are today going with an overview of Java. As in all other computer languages, the elements of Java do not exist in isolation. Rather, they work together to form the language as a whole. However, this interrelatedness can make it difficult to describe one aspect of Java without involving several others. Often, a discussion of one feature implies prior knowledge of another. For this reason, this chapter presents a quick overview of several key features of Java. The material described here will give you a foothold that will allow you to write and understand simple programs. Most of the topics discussed will be examined in greater detail in remaining chapters of Part 1. Object-Oriented Programming. Object-Oriented Programming (OOP) is at the core of Java. In fact, all Java programmers are to at least some extent object-oriented programs. Okay. OOP is so integral to Java that it is best to understand its basic principle before you begin even writing simple Java programs. Therefore, this chapter begins with a discussion of theoretical aspects of OOP. Two paradigms. All computer programs consist of two elements, code and data. Right. Furthermore, a program can be conceptually organized around its code or around its data. That is, some programs are written around what is happening and others are written around who is being affected. Okay. These are the two paradigms that govern how a program is constructed. The first way is called process-oriented model. This approach characterizes a program as a series of linear steps, that is code. Okay, the first way is called process-oriented model. Characterizes a program as the process-oriented model can be thought of code acting on data. Procedural languages such as C employ this model to considerable success. However, as mentioned in chapter 1, problems with this approach appear as programs grow larger and more complex. To manage increasing complexity, the second approach, called object-oriented programming, was conceived. Object-oriented programming organizes a program around its data, that is, its object, and a set of well-defined interfaces to that data. An object-oriented program can be characterized as data controlling access to code. As you will see, by switching the controlling entity to data, you can achieve several organizational features. Okay, abstraction. An essential element of object-oriented programming is abstraction. Humans manage complexity through abstraction. For example, people do not think of car as a set of tens of thousands of individual parts. They think of it as well-defined object. Okay. Well-defined object with its own unique behavior. This abstraction allows people to use a car to drive to the grocery store without being overwhelmed by the complexity of the individual parts. They can ignore the detail of how the engine, transmission, braking system work. Instead, they are free to utilize the object as a whole. A powerful way to manage abstraction is through the use of hierarchical classifications. This allows you to layer the semantics of complex systems, breaking them into more manageable pieces. From the outside, the car is a single object. Once inside, you see that car consists of several subsystems steering, brakes, sound system, seat belts, heating, cellular phone. In turn, each of these subsystems is made up of more specialized units. For instance, the sound system might consist of a radio, a CD player, and/or MP3 player. The point is that you manage the complexity of car or any complex system through the use of hierarchical abstraction. Hierarchical abstractions of complex systems can also be applied to computer programs. The data from a traditional process-oriented program can be transformed by abstraction into component objects. A sequence of process steps can become a collection of messages between the objects. A sequence of process steps can become a collection of messages between the objects. Thus, each of these objects describes its own unique behavior. You can treat these objects as concrete entities that respond to message telling them to do something. Okay. Object-oriented concepts from the heart of Java, just as they form the basis for human understanding. It is important that you understand how these concepts translate into programs. As you will see, object-oriented programming is a powerful and natural paradigm for creating programs that survive the inevitable changes accompanying the life cycle of any major software product, including consumption, growth, and aging. For example, once you have well-defined objects and clean, reliable interfaces to those objects, you can gracefully decommission or replace parts of an older system without fear. The 3OOP principle. All object-oriented programming languages provide mechanisms that help you implement an object-oriented model. Their encapsulation, inheritance, and polymorphism. Let us take a look at these concepts now. Encapsulation. Encapsulation is the mechanism that binds together code and data it manipulates and keeps both safe from outside interference and misuse. One way to think about encapsulation is a protective wrapper that prevents the code and data from being arbitrarily accessed by other code defined outside the wrapper. Access to the code and data inside the code is tightly controlled through a well-defined interface. To relate to the real world, consider the automatic transmission on an automobile. It encapsulates hundreds of bits of information about the engine, such as how much you are accelerating, the pitch of the surface you are on, and the position of the shift lever. As you, as a user, have only one method of affecting this complex encapsulation: by moving the gear shift lever. You can't affect the transmission by using a turn signal or windshield wipers, for example. Thus, gear shift lever is a well-defined, indeed unique interface to the transmission. Further, what occurs inside the transmission does not affect objects outside the transmission. For example, shifting gears does not turn on headlights because an automatic transmission is encapsulated, Dozens of manufacturers can implement one in any way they please. However, from the driver's point of view, they all work the same. This same idea can be applied to programming. The power of encapsulated code is that everyone knows how to access it and thus can use it regardless of the implementation details. And without fear of unexpected side effects. In Java, the basis of encapsulation is the class. Although the class will be examined in a great detail later in this book, the following brief discussion will help you now. A class defines the structure and behavior that will be shared by a set of objects. Each object of a given class contains the structure and behavior defined by the class as if it was stamped out by a mold in the shape of the class. For this reason, objects are sometimes referred to as instances of a class. Thus, a class is a logical construct and an object has physical reality. When you create a class, you will specify the code and data that constitute that class. Collectively, these elements are called members of the class. Specifically, the data defined by the class are referred to as member variables or instance variables. The code that operate on the data is referred to as member methods or just methods. In properly written Java programs, the methods define how the member variable can be used. This means that behavior and interface of a class are defined by the methods and operates on its instance data. Since the purpose of a class is to encapsulate complexity, there are mechanisms for hiding the complexity of the implementation inside the class. Each method or variable in a class may be marked private or public. Right. The public interface of a class represents everything that external users of the class need to know or may know. The private methods and data can only be accessed by code that is a member of the class. Therefore, any other code that is not a member of the class cannot be accessed by private methods or variables. Since private members of the class may only be accessed by other parts of the programs through the class public methods, you can ensure that no improper action can take place. Of course, this means that public interface should be carefully designed not to expose too much of the inner working of a class. Inheritance. Inheritance is the process by which one object acquires the property of another object. This is important because it supports the concept of Is it recording? Yeah, okay, so it is just recording this, right? Yeah, because I'm not recording. Yeah, okay, so it is only recording the capture. Right. This is important because it supports the concept of hierarchical classification. As mentioned earlier, most knowledge is made manageable by hierarchical, that is, top down classifications. For example, a golden retriever is part of the classification dog, which in turn is part of the mammal class, which in turn is under the larger class animal. Without the use of hierarchies, each object would need to define all of its characteristics explicitly. However, by use of inheritance, an object need only define those qualities that makes it unique within its class. Okay. It can inherit its general attributes from its parents. Thus, it is the inheritance mechanism that makes it possible for one object to be a specific instance of a more general case. Most people naturally view the world as made up of objects that are related to each other in a hierarchical way, such as animals, mammals, and dogs. If you wanted to describe animals in an abstract way, you would say that they have some attributes such as size, intelligence, and type of skeletal system. Animals also have certain behavioral aspects. They eat, breathe, and sleep. This description of attributes and the behavior of the class is the class definition for animals. Um, okay. Okay, nice. Okay, if you wanted to describe a more specific class of animals, such as mammals, they would, such as mammals, they would have more specific attributes such as type of teeth and mammary glands. This is known as a subclass of animals, where animals are referred to as mammals superclass. Okay. Since mammals are simply more precisely specified animals, they inherit all of the attributes from animals. A deeply inherited subclass inherits all of the attributes from each of its ancestors in the class hierarchy. Inheritance interacts with encapsulations as well. If a given class encapsulates some attributes, then any subclass will have the same attributes plus any that adds as a part of its specialization. Okay. This is a key concept that let object-oriented programs grow in complexity linearly rather than geometrically. A new subclass inherits all of the attributes of its ancestors. It does not have unpredictable interaction with the majority of the rest of the code in the system. Okay. Polymorphism. Polymorphism, from Greek meaning many forms, is a feature that allows one interface to be used for a general case of actions. The specific action is determined. Okay. The specific action is determined by the exact nature of the situation. Consider a stack. You might have a program that requires three types of stack. One stack is used for integer values, one for floating point values, and one for characters. The algorithm that implements each stack is the same, even though the data being sorted differs. In a non-object oriented programming, you would be required to create three different set of stacks routines, with each set using different names. However, because of polymorphism in Java, you can specify a general set of stack routines that all share the same names. Okay. Okay. More generally, the concept of polymorphism is often expressed as by the frame one interface, multiple methods. This means that it is possible to design a generic interface to a group of related activities. This helps reduce complexity by allowing the same interface to be used to specify a general class action. Okay. It is a compiler's job. It is a compiler's job to select the specific action, that is method, as it applies to each situation. You, the programmer, do not need to make the selection manually. You only need to remember and utilize the general interface. Extending the dog analogy, a dog's sense of smell is polymorphic. If the dog smells a cat, it will bark, run after it. If the dog smells its food, it will salivate and run to its bowl. The same sense of smell is at work in both situations. The difference is what is being smelled. That is the type of data being operated upon by the dog's nose. This same general concept can be implemented in Java as it applies to methods within a Java program. When properly applied, polymorphism encapsulation and inheritance combine to produce a programming environment that supports the development of far more robust and scalable programs that does the process-oriented model. Okay, than does the process-oriented model. A well-designed hierarchy of classes is the basis for using the code in which you have invested time and effort developing and testing. Encapsulation allows you to migrate your implementation over time without breaking the code that depends on the public interfaces of a class. Polymorphism allows you to create clean, sensible, readable, and resilient code. Of the two real-world examples, the automobile more completely illustrates the power of object-oriented design. Dogs are fun to think about from an inheritance standpoint, but cars are more like programs. All drivers rely on inheritance to drive different types of subclasses of vehicles, whether the vehicle is a school bus, a Mercedes sedan, a Porsche, or the family minivan. The driver can more or less find and operate the steering wheel, the brakes, and accelerators. After a bit of gear grinding, most people can even manage the difference between a stick shift and an automatic because they fundamentally understand the common superclass, the transmission. People interface with encapsulated features on cars all the time. The brake and the gas pedals hide an incredible array of complexity with an interface so simple you can operate them with your feet. The implementation of the engine, the style of brakes, and the size of the tires have no effect on how you interface with the class definition of the pedals. The final attribute, polymorphism, is clearly reflected in the ability of car manufacturers to offer a wide array of options on basically the same vehicle. For example, you can get an anti-lock braking system or traditional brakes, power or rack and pinion steering, a 4-6 8-cylinder engine. Either way, you will still press the brake pedals to stop, turn the steering wheel to change the direction, and press the accelerator when you want to move. The same interface can be used to control a number of different implementations. As you can see, it is through the application of encapsulation, inheritance, and polymorphism that the individual parts are transformed into the object known as car. The same is also true of computer programs. By the application of object-oriented principles, the various parts of a complex program can be brought together to form cohesive, robust, and maintainable whole. As mentioned at the start of this section, every Java program is object-oriented, or put more precisely, every Java program involves encapsulation, inheritance, and polymorphism. Although the short example programs shown in the rest of this chapter and in the next few chapters may not seem to exhibit all of these features, they are nevertheless present. As you will see, many of the features supplied by Java are part of its built-in class libraries, which do make extensive use of encapsulation, inheritance, and polymorphism. A first simple program. Now that the basic object-oriented underpinning of Java has been discussed, let's look at some actual Java programs. Let's start by compiling and running the short sample shown here. As you will see, this involves a little more work than you might imagine. Okay, this is a simple program. Call this file examples.java. Okay, so we will switch. Okay, then now I am going to type it into the program. So we go here, Java, GitHub, Java the computer reference, basic. Let me just make a new chapter 2. An overview of Java and first simple program. Let's open this sample.java. Okay, so I am going to start here. This is a simple Java program. Call this file sample.java. Then we start with class example. Then we start your program begins with a call to main function. Then you go public static void main, capital S, string args, and then you go system.out.println. This is a simple Java program. Okay, so that is it. Entering the program. For most computer languages, the name of the file that holds the source code to a program is material. However, this is not the case with Java. The first thing that you must learn about Java is that the name you give to a source file is very important. Okay. For example, the name of the source file should be example.java. Let's see why. In Java, a source file is officially called a compilation unit. It is a text file that contains, among other things, one or more class definitions. For now, we will be using source file that contains only one class. The Java compiler requires that a source file uses the Java file name extension. Okay, compilation unit. As you can see by looking at the program, the name of the class defined by the program is also example. This is not a coincidence. In Java, all code must reside inside a class. By convention, the name of the main class should match the name of the file that holds the program. Okay. You should also make sure that the capitalization of the file name matches the class name. The reason for this is that Java is case sensitive. Okay. At this point, the convention that file names correspond to class name may seem arbitrary. However, this convention makes it easier to maintain and organize your programs. Furthermore, as you will see in later chapter, in some cases it is required. Then we go compiling the program. To compile the example program, execute the compiler javac specifying the name of the source file. Example C. Okay. The javac compiler creates a file called example.class that contains the bytecode version of the program. As discussed earlier, the Java The Java bytecode is the intermediate representation of a program that contains instructions the Java virtual machine will execute. Thus, the output of Java C is not code that can be directly executed. To actually run the program, you must use the Java application launcher called Java. To do so, pass the class name example as a command line argument as shown below. Okay. So let's do so real quickly. Okay, so we will go here. Java C example.java. Then if you see, we have example class file, Java application launcher, and the name of the class. This is a simple Java program. Okay, great. When Java source code is compiled, each individual class is put into its own output file. When Java source code is compiled, each individual class is put into its own output file, named after the class and using the class extension. Okay. This is why it is a good idea to give your Java source file the same name as the class they contain. The name of the source file will match the name of the class. Okay. .class file. When you execute Java as shown, you are actually specifying the name of the class that you want to execute. It will automatically search for a file by that name that has the .class extension. If it finds the file, it will execute the code contained in the specified class. Note: beginning with JDK 11, Java provides a way to run some type of simple programs directly from source file without explicitly invoking Java. See, this technique can be useful in some situation. For the purpose of this work, it is assumed you are using normal compilation process just described. Okay. A closer look at the first sample program. Although example.java is quite short, it includes it includes several key features that are common to all Java programs. Let's closely examine each part. The program begins with the following line. This is a comment. Like most popular programming languages, Java lets you enter a remark into the program's source file. The contents of the comment are ignored by compiler. Instead, a comment describes or explains the operation of the program to anyone who is reading its source code. Okay. In this case, the comment describes the program and reminds you that the source file should be called example.java. Of course, in real applications, comments generally explain how some part of the program works or what a specific feature does. Java supports three styles of comments. The one shown at the top of the program is called a multi-line comment. This type of comment must begin with /* and ends with */ Anything between these two comment symbols is ignored by the compiler. As the name suggests, a multi-line comment may be several lines long. The next line of code in the program is shown here, class example. This line uses a keyword class to declare that a new class is being defined. Example is an identifier that is the name of the class. The entire class definition, including all of its members, will be between the opening curly and closing curly braces. Okay. For the moment, don't worry too much about the details of a class, except to note that in Java, all programs activities occurs within one. This is one reason why all Java programs are at least a little bit object oriented. The next line in the program is a single line comment. This is the second type of comment supported by Java. A single line comment begins with a double forward slash and ends at the end of the line. As a general rule, programmers use multi-line comments for longer remarks and single-line comment for brief line-by-line descriptions. The third type of comment, a documentation comment, will be discussed in the comment section later. Okay. The next line of code is shown here. Public static void main string args. This line begins with main method. As a comment preceding it suggests, this is the line at which the program will begin executing. As a general rule, a Java program begins executing by calling main. The full meaning of each part of this line cannot be given now, since it involves a detailed understanding of Java's approach to encapsulation. However, since most of the examples in the first part of the book will use this line of code, let's take a brief look at each part now. The public keyword is an access modifier, which allows the programmer to control the visibility of the class members. When a class member is preceded by public, then that member may be accessed by code outside the class in which it is declared. Okay. In this case, main must be declared public, since it must be called by code outside of its class when the program is started. The keyword static allows main to be called without having to instantiate a particular instance of class. This is necessary since main is called by the Java virtual machine before any objects are made. The keyword okay. So without making an object, we can call main function if it is a static. The keyword void simply tells the compiler that main does not return a value. As you will see, methods may also return values. If all this seems a bit confusing, don't worry, all these concepts will be discussed in detail in subsequent chapters. As stated, main is the method called when Java application begins. Keep in mind that Java is case sensitive, thus main is different than main. It is important to understand main with a capital M. It is important to understand that the Java compiler will compile classes that do not contain a main method, but Java has no way to run these classes. So if you had typed main instead of main, the compiler would still compile a program. However, Java would report an error because it would be unable to find the main method. Okay. Any information that you need to pass to a method is received by variables specified within the set of parentheses that follow the name of the method. Right. That follow the name of the method. These variables are called parameters. If there are no parameters required for a given method, you still need to include the empty parentheses. Right. In main, there is only one parameter, albeit a complicated one. String args declares a parameter named args, which is an array of instances of the classes. String arrays are a collection of similar objects. Objects of type string store character strings. In this case, args receives any command line argument present when the program is executed. This program does not make use of this information, but other programs shown later in the book will. Okay. And we move on to the last character on the line is that opening curly brace. This signals the start of main's body. All of the code that comprises a method will occur between the method's opening curly brace and its closing curly brace. One other point, main is simply a starting place for your program. A complex program will have dozen of classes, only one of which will be needed to have main method to get things started. Furthermore, for some type of programs you won't need main at all. However, for most programs shown in this book, main is required. Okay. The next line of code is shown here. Notice that it occurs inside main. System.out.println quote start double quote start. This is a simple program, full stop, double quote end, parenthesis, closing parenthesis, and semicolon. This line outputs the string "this is a simple Java program" followed by a new line on the screen. Output is actually accomplished by built-in println method. In this case, println displays the string which is passed to it. As you will see, println can be used to display other types of information too. The line begins with system.out. While too complicated to explain in detail at this time, briefly, system is a predefined class that provides access to the system, and out is the output stream that is connected to the console. As you have probably guessed, console output and input is not used frequently in most real-world Java applications. Since most modern computing environments are graphical in nature, console I/O is used for simple utility programs, demonstration programs, and server-side code. Later in this book, you will learn other ways to generate output using Java. But for now, we will continue to use the console I/O methods. Notice that println statement ends with a semicolon. Many statements in Java end with a semicolon. As you will see, semicolon is an important part of Java syntax. the first parenthesis, the first curly brace is the program ends main, and the last curly brace ends the example class definition. So that is it for today.